Today, I'm going to be introducing you to structural equation modeling. I've been hinting at this across this semester, but this is really the next step. Once you get the basics in regression and ANOVA and factor analysis, you're ready to begin learning about SEM or structural equation modeling. So today I'm going to kind of introduce this to you and kind of give you the basics and hopefully give you enough that if you wish to explore this on your own, you have enough grounding to do that. And for those who are going on to the SEM class in the fall, that you get a little bit of an introduction to it. So normally if we were in class, I'd ask you these questions. So I'd like you to kind of think this for yourself for a little bit. But what has made the statistics we have studied thus far challenging for you? What have been the biggest limitations of the statistics we have studied so far, and what would make it easier? Often when I talk to students about these, some of the things that they talk about are the complexity of trying to figure out how to run it, which boxes to check, where to go in the menus, trying to choose which model to do, whether you're doing logistic regression or ANOVA or factorial ANOVA, and also the syntax can be pretty complicated for some of these. As far as the biggest limitations, some of the main limitations are that you're limited on the number of variables you can choose. So you really have to think about, like if you're doing linear regression, you can't have more than one dependent variable. If you're doing ANOVA, you can't have more than one covariate. And the way it works with the dependent variables, it combines them all together. And that can make it more limiting on you and the kinds of questions that you ask by limiting the variables that you can ask for. In addition, if you remember way back at the beginning of the semester when we talked about missingness, a huge limitation around missingness is that SPSS only uses pairwise and listwise deletion. So if you remember that FIML, that full information maximum likelihood, none of the statistics that we've run thus far is actually using a style or a method of missingness that is contemporary and that also has the assumptions for the statistics that we're doing. So remember that MAR, missing at random, that we have most of our research that we're using has missingness at random. And so not being able to do that is a huge limitation. Your inability to handle missingness really increases that error. And remember, everything that we've talked about is all about reducing error so that we can have a more certain about our effect in our models. So by using a method of missingness that actually amplifies the error is a huge limitation on using linear regression ANOVA and SPSS. So as we move into SEM, we're going to be able to use those more sophisticated methods for handling missingness that will actually reduce for error. And some other things, what would make it easier for you is actually making the syntax really simple. In SEM, the syntax is actually far more simple than it is in SPSS with any of the analyses you do in there. So, what if you could only need to use SPSS as a data management software? So all you're doing is the reverse coding, running some of your assumptions around frequencies, creating dummy coded variables, cleaning your data. That's all you're using SPSS for. You're not using it for any of your actual statistics that you're going to be running. What if you could draw out your model on a piece of paper and test exactly that? So draw out what you want. Take your research questions and draw it out and actually test exactly what you want to do. What if you could use pictures instead of tables to explain your results? So all semester, a lot of you had been challenged by creating tables and figuring out how to create the tables. When we get in SEM, you don't have to use tables to report your results. You can actually use pictures instead of tables. And pictures are often much easier to get across what you're trying to show than tables. And what if you can use as many independent, dependent, moderator, mediator variables as you want with whatever kind of data you want? So you're not going to be limited based on the analysis that you're doing. The only limits you'll have are on your own ability to really develop thoughtful, sophisticated research questions. And once that is your limitation, you can all of a sudden do great research because you wouldn't be in this program, you wouldn't be in this class if there were any kind of limitations on that. Once you're able to really explore what you want to do and draw out what you want to do and collect the data you want to collect and run that kind of a model, all of a sudden we can be doing very sophisticated, important, and meaningful work. And also, Longitudinal data. That is a huge piece of what we need to be doing in social sciences, is actually testing longitudinal data. Once you get into SEM, testing longitudinal data becomes not only more easier, it also becomes more precise, and it also becomes, again, more sophisticated because you can do things with this, like looking at trajectories across time that are much more difficult or that you cannot do in simple linear regression. And in addition, you can combine both ANOVA and regression in a single analysis. So you want to test group differences by also having regression in there. You can do that with SEM. So this is my kind of way about how I describe it. But everything you've learned thus far has been like learning your grammar, your ABCs. You're learning about the fundamentals and how things work. You're learning about regressions and factor loadings and ANOVAs. It's all about learning the inner workings of how it works. That's like grammar. It's the inner workings of how language work. Some people really love learning about grammar, but most people find it difficult or boring. Statistical modeling, once you get into modeling such as SEM, to me this is like writing poetry. And this is really where the fun really starts. It's where you can now all of a sudden be doing really cool things with your work and also be doing things that are very powerful and easy to explain. So let's kind of introduce SEM to you. So the scholarly explanation of SEM is that it is a family of statistical procedures, such as path analysis, confirmatory factor analysis, analysis of mean structures, and latent growth modeling, that takes a confirmatory approach to the analysis of a structural theory bearing on some phenomena. The more understandable explanation, so I would call this like the grad level understanding of this, is that SEM is a set of statistical analyses that allows us to describe the structure of the data in a simple way that is understandable and interpretable. So we posit and test models, and then we explain the relationships among a set of variables. So that can be mediating, moderating effects, group effects, effects on one variable on another. Now when we bring that down one more level to the grandma explanation, it's a statistical technique with a lot of flexibility to test a wide variety of hypotheses and models. One of the most important things about learning SEM is it does open up your mind, and it opens up your possibilities to new kinds of questions that you perhaps might not have thought about before. So why do we do SEM? What is the purpose of it? The purpose is to describe the structure of the data, and by the structure we're looking at how variables are related to each other in a simple way so that it's understandable and interpretable. And when we're doing SEM, it involves postulating. So we're going to be proposing and testing models that explain relationships among a set of variables. We may have multiple latent constructs or variables. We can have multiple dependent variables, independent variables, mediators, moderators. And lastly, SEM provides a means of assessing whether the hypothesis model fits the data. Ultimately, that's what we're going to be doing. We're going to be proposing a model, and then we're going to get some information to tell us how well that model fits the data. So just like you did in linear regression, when we looked at our model fit indices of R squared and the ANOVA test, you are going to get a set of fit indices, so statistics that tell you how well that model fits the data. If it fits it well, we can reasonably say that this is a good relationship of these variables to each other, because we're proposing that this variable causes this other variable, or is impacted by it, or influences this other variable, or that this is a mediating variable. And what our output will tell us is not only what are those regressions or those path coefficients, but it will also tell us how well that fits the data. So at its core, SEM provides a way for us to assess whether the hypothesized model fits the data. So a lot like we did in regression. Does the model that we are proposing fit the data well? If it fits the data well, then we can reject that null hypothesis that this model doesn't work and accept that this is a good way to present this data and a good way to present these variables to each other, these relationships that we have proposed. So benefits of SEM: one, it takes a confirmatory approach rather than an exploratory approach. And today in social sciences, most of what we're doing is confirmatory. We're saying, here is what our hypothesis is. Now let's confirm that this works. We can use multiple independent, dependent, mediator, moderator variables. We can control for many, many other variables that can impact results. So, however many control variables you want, as long as you have the power to have that, you have enough participants, you can have those in there. Additionally, something we have not done at all yet this semester is you can test variables as measured or as latent. So measured just means you have the variable right there in your data. So we've done that with composite variables and individual variables. Latent variables, you're actually creating a brand new variable from these other ones in the model. And I'll talk a little bit about that in a moment here, but there's a lot of power in being able to represent things that we cannot directly measure. That's what you're doing when you create a latent variable. And oftentimes, latent variables offer a much more realistic way to model things social scientists are interested in, because we're often interested in things that we cannot directly measure, but rather we measure things that are indicators of that. So latent variables offer a powerful way for us to measure those kinds of things. Also, we can test the most complex, fully developed theories, hypotheses, and ideas in a parsimonious, easily interpretable model. So we can look at time sequencing of variables, mediating variables, and including their indirect and direct effects. So if you remember when we covered mediation, we couldn't measure the indirect and the direct effects. In SEM, you can do that. You look at moderating effects, and group differences. So you're able to do a lot of these things in a way that is easily interpretable and parsimonious. And we can handle missingness with precision and sophistication. So we can use full information maximum likelihood. Also, one of the biggest benefits of SEM is how it measures and accounts for error. We are better able to account for error in SEM in a way that nothing in SPSS can do. So because of that, because we can account for error much better and in a much more accurate way, we're going to be able to find our results more accurately because they won't be obscured by inflated error. So at this point, I would say pause this, find someone, and answer these questions for them. So what is SEM? What is the purpose? And what are the benefits? And try and explain these to someone, either a classmate or a friend, or someone in your house. So some things that you need to know before doing SEM. 1, SEM combines everything you've learned thus far. So correlations, t-tests, chi-squareds, ANOVAs, factor analyses, regression, everything that you've learned from your first stats class up to now, it combines all of this information. So you need to have that information in order to move forward. Most especially, you need to have a solid background in variance, correlation, regression, factor analysis, reliability, and validity. So you need to have good research methods background and a strong background in variance, correlation, regression, and factor analysis. It's one of the reasons I've tried to hammer those across this semester and really make sure to the best I can that you have understood these things, because you're going to need these when you go into SEM, because especially variance and regression, you're going to be doing a lot of that in SEM. Also, SEM is a powerful tool, and as with any analysis, we want to make sure that you adequately understand it before you're using it. So remember, with great power comes great responsibility. It's a powerful tool, so you got to know how to use it well and use it right. So just like all of the other statistics we've talked about, everything has assumptions. So in SEM, we have all the assumptions that we're used to, all the assumptions of normality, multivariate normality, linearity, independence, homoscedasticity of relationships. We're going to add one more onto that, which is having a specified model. You need to have the model that's specified correctly. So that means you do need to have the predictors or the variables in there that should be in there, and don't include ones that shouldn't be in the model. And that when you draw that out, it's drawn out in a way that's also parsimonious, in a way that makes sense and is helpful. So model specification would be something we would cover in an entirely different lecture. So like for those going on into the fall for the SEM class, we'll talk a lot about model specification. We'll probably spend a whole day on model specification. So in SEM, similar to like ANOVA, where you have your factorial ANOVA and you have your repeated measures ANOVA, there's a lot of different kinds of SEM models. Now keep in mind, you don't really need to know this in order to run it or in order to know which way you need to go to, because that doesn't matter at all when you're running it. This is only helpful for you when you see people write up analyses, because they may not say they did a structural equation model. They may say, I did a path analytic model. This is just an SEM model without latent variables. Or they may say, I did a confirmatory factor analysis model. That would just be a CFA, which is done in SEM. Or they may say a full latent model or an autoregressive model, latent growth, growth mixture. They're just different kinds of models that people have named in order to better understand and explain to other people. This is not like an SPSS where you need to know these in order to run your model, but it is helpful to know these to understand when you have a hypothesis, what's the best way to draw this out? Because these are all kind of drawn in different ways. Like an autoregressive model, that looks at the stability of variables across time and how they interact with each other. So you may look at like how does alcohol use change across time and its association with like parental strain or relationship strain, where you can look at how does this look across time and also how they impact each other. So we're able to account for the variable in the past and how it influences in the future while also looking at a covariate. Latent growth modeling is really all about trajectory. So it's starting from a starting place and then looking at how something changes across time. So when we look at things like trajectories of marital happiness, trajectories of delinquent behavior, you're starting with some event or time frame and then modeling out how does that look across time and what are the variables that account for differences in that trajectory. Growth mixture modeling is just like latent growth modeling, where instead of just looking at trajectory across time, we're looking at different groups within that trajectory. So like with one of my mentors did a lot of work around the transition to parenthood, and he did a lot of growth mixture modeling where he would look at that trajectory of the different groups, the people that stayed happy and got happier across the transition to parenthood, some whose happiness totally dropped off the map, and some who just kind of slowly declined. And through the growth mixture modeling, you can determine what is related to those three different kinds of trajectories. So when you're running SEM, there's just a few steps to run it and to run it well. One, start with good data. So select measures, collect, screen, prepare the data. Like we talked about at the beginning of the semester, garbage in, garbage out. So you want to start with really good data. Number two, specify the model. That's saved for a different lecture when we get into that, but it's just making sure that you have a good parsimonious model that's specified accurately. Three, determine if the specified model is identified. So when we talk about model identification, that's also another lecture, but that's just making sure that you have enough degrees of freedom in there to make the model interesting. Number four, estimate the model. So that means you're actually running it in M+ or a similar software program. So you're gonna run the model, evaluate it, interpret the model, the parameter estimates, that's the regression coefficients, and also make sure you're considering equivalent or alternative models that may be different and may be a better explanation of the data. Number five, respecify the model if there's a problem in step 4, and then you're going to report the results, replicate the results, and apply the results. So now I'm going to talk about the symbols in SEM. And what I said earlier is that you can draw this out. There are some rules around how you draw this out so that when you draw it, everybody knows what everything means in there. And there are really just 5 simple things when you're drawing. One is your square. So your square, your rectangle, rectangle will be if your word is much bigger. That represents a measured or observed variable. So that's a variable that's like a line item in SPSS or a composite variable. A latent variable is what I was talking about earlier. So that's a variable that is made up of several observed variables or manifest variable. And then you'll sometimes see in models, they don't always put it in the picture because it's not always necessary. But the circle with an E in it or circle with it'll actually say error in it, that's just an error term. And that's included in there because, like I said before, we're actually accounting for error in a more precise way. So our error terms may be part of the model. And then when we're connecting variables together, we'll either have a straight line or we'll have a curved line. A curved line represents that this is a correlation. So this is just your R, your Pearson's correlation. A straight line is either going to be a regression coefficient, which in SEM they just call a path coefficient, but it's a regression coefficient, or it may be a factor loading if it's a latent variable. A latent variable will have those observed variables going into it. We call those factor loadings. So it'll either be a factor loading or it'll be a regression coefficient. As you look at this, you should be able to look at these and name that symbol. So you can see these two circles here. Those are going to be latent variables. The squares all here are going to be measured variables or manifest variables. This curved line is going to represent a correlation. So when you run your model, you'll have a value for this. And then this one here would be your path coefficient, which would be a regression coefficient. So now some of the language in here, because we are going to introduce some new language. Like with anything, we want a common language so that we can talk in a way that everybody understands. So one thing, like I've said before, already talked about before, is observed or manifest variables versus latent variables, or factors or constructs. A manifest variable is a directly observed or directly measured variable, where latent constructs are not directly measured. So like in here, so here's another example where we have observed variables. These are all manifest variables. We have our error term on here. And like I said before, we can actually account for error really well in this. And one of the ways we can do that is we can actually put on here, we can put a correlation here and actually correlate these two errors. So if the error between two variables is related, we can actually account for that by having that correlated with each other in the model and better account for the shared error variance between these variables. And then this curved line here would represent that we're accounting for the correlation between these two variables, something you cannot do in linear regression in SPSS. We'd have our straight lines here, which represent our path coefficients, which is our regression coefficients. So you can see these other two over here, these are just kind of factor loadings because this is indicating that the error is there. So here's a latent variable, an example of one. So we would have like financial situation, and we're not actually measuring that. We're measuring that by measuring these indicators of it. So our income, debt to income ratio, and making our ends meet. So you can see that the arrows are going away from it. This is a really good way to kind of show that these are actually factor loadings rather than regression coefficients. So types of variables in SEM. In SEM, we don't really use the language of independent and dependent variables because it doesn't really make much sense in a lot of the models we're using in SEM, but rather the language we use tends to be with exogenous and endogenous variables. So exogenous variables, what that means, so exo means coming from the outside. So in other words, exogenous variables have arrows going out, but none going in. So they're going to be at the beginning of the model. Endogenous variables is any variable that has an arrow going into it. So those can be variables that are in the middle, that are in the end, that are in other places. But if it's not at the beginning, it's an endogenous variable. So for example, in this one, we have here on the far left side are exogenous variables because there's nothing going into it. They're at the beginning of our model. And then these other three would all be endogenous variables because they have something going into it. So you'll sometimes see papers where they talk about exogenous, endogenous variables. So when you see those, I put this in here so you won't be confused. Oftentimes they will say, like here's our independent, here's our dependent, and here are two mediating variables. But just so you know that when you're reading about SEM or when you're reading some articles and you see those terms, you know what they mean. So if we were in class, I'd actually have you draw out a model, take a research question you have, draw it out, put everything you're interested in there, control variables, independent variables, mediators, moderators, dependent variables, groups that you may want to look at, or differences between groups. Make sure you get all the complexity that you want and that would really fit the research and make it truly rigorous. This is one thing that's going to really make your research to be able to really pop out, be meaningful, and also be published in high impact journals. And so I would encourage you right now to just pause the video and do that, because we're going to come back to that when we get to syntax later on in this lecture, so you can draw it out. All right, some other language that you'll hear about in SEM, we talk about recursive and non-recursive models, measurement model, structural model. So recursive model just really means that it's unidirectional. So like you saw in the ones before, we go left to right. No circles. So a non-recursive model means it's a model with feedback loops, so we have circles in there. That's bad. You cannot do any models that are non-recursive. It needs to go in one direction. Just like we read left to right, the models need to go left to right. The measurement model, that's a model evaluating the components of the latent variable. So with nothing predicting another latent variable. So what we're really just looking at is just the latent part of the variable. or of the model. So whenever you have latent variables in a model, you kind of need to test that part separate to make sure it works well. The structural model is then where at least one latent variable is predicted or used as a predictor. So that's really the main part of your model. Kind of used this language earlier, but model specification and identification. Specification is just making sure that you've drawn it out in a way that follows the parameters. We go left to right. There's no circles or feedbacks. Model identification is how many errors you have in there. Or, sorry, not errors, arrows. So model identification is all about how many arrows you have in there. A justified model means you have no degrees of freedom. So you have all the arrows in there that you can possibly have. And it will always fit the data perfectly because there's a perfect relationship that you've proposed. Over-identified means you actually have too many arrows in there, more arrows than can be possible. And under-identified means that you have too many parameters for what is in the covariance matrix. So we'll talk about model identification at a different time if you're taking the class in the fall. If you get into SEM and if you want to do SEM, it's important to read a chapter or two about model identification, because that's just some important pieces about how to draw a model out that will work, but also, and most importantly, that's parsimonious and is also helpful in the analysis. We talk a lot about model fit. So just like we've been talking about back in regression, when we talk about how we're going to propose a model and how it fits the data, we talk a lot about model fit. We've talked about parameters in there, and in there you can do freely estimated, you can fix them at a certain value, you can strain parameters to be equal to each other. This becomes important later when you're getting into like dyadic analyses and other kinds of things. But just helping you to just introduce yourself to some of the language that we're using in here, because it's a new model, we're going to have new languages and new words that we're going to use. In your model modification, that's just adjusting different pieces around your model. And then in your model, when you're doing mediation, you're going to have direct and indirect effects, and then the total, which is the direct plus the indirect together. All right, so now I want to show you some examples of SEM models. I think all of these are from papers that I've done, so that I can actually show you some of the stuff that I've done and talk about it a little bit more with a little bit more expertise. So this is a paper that I did with Cole Ratcliffe. This is actually the paper that he developed in our SEM class when I was in our doc program. So I wanted to present this to you because this is something a doc student did while in a doc program. This is not beyond any of you, and this was using the Fragile Families data set, so a secondary data set that's open and publicly available, and some of you were going to use for your paper. So in this one, he looked at mother relationship quality and father relationship quality, and how that impacted positive engagement with their child 2 years later. So this is a longitudinal analysis. We're looking at from the child's age 1, 3, 5, and 9, and then how that positive engagement impacted negative child behavior 2 years later, while also looking at how parental or relationship quality, mothers and fathers' reports of their relationship quality, impacted negative child behavior 4 years later. So the idea behind this is, man, if we can get at parents when their child is 1, are we going to be able to help that child by the time they're entering kindergarten, when they're 5 and entering kindergarten? So if we can intervene really early through good couple therapy and really improve their relationship, does that have an impact on that child's behavior 4 years later? And so if you're looking at this model, you can see in here we have our straight line, so that means regression coefficient. We have our curved line, which is indicating correlation. So what we're doing here is we're actually accounting for the correlation, so the shared variance between these variables, because mothers and fathers' reports of relationship quality and their positive engagement with their child will be related to each other. So we can see here that indeed mother's relationship quality is positive related to positive engagement. So this reads just like a linear regression like we talked about before. So as mother's relationship quality goes up by 1 standard deviation, 2 years later, mother's positive engagement goes up by 0.44 standard deviations, while controlling for father's relationship quality. We can also see that as mother's relationship quality goes up, this is negative 0.17, so their negative child behavior, and we have our asterisk here that says it is significant, goes down by 0.17 standard deviations, while controlling for mother's positive engagement at age 3. So what we can see here is that if we can get couples into therapy and help them with their relationship quality, when that child is 1, that 4 years later, that child will have fewer negative behaviors. And also 2 years later, mothers will be more positively engaged, fathers will be more positively engaged, and that mother's positive engagement also reduces it. So if we get them in at age when that child is 1, we can reduce their negative child behavior 4 years later, and we can also have an indirect influence on that. Here's our indirect path through more positive engagement 2 years later. So this is a really powerful study that gives us and by presenting it here in this picture, you can see it and you can see the power behind early intervention in couples to help children many, many years later. So this one here, this was actually my master's thesis. So I was really interested. This was back in, this would have been, it was published in 2014, but I did my thesis in probably 2012, I'm thinking, or 2009. So this was, Facebook was newer at this time, and there was a lot of infidelity happening by people getting involved in relationships online. So I was really curious about the relationships between relationship satisfaction and trust, and on people's behaviors in their relationships. So you can see here I have 2 latent variables. And fidelity, this is what I called fidelity, was made up of no former partners and no flirting. So this was an item that asked, like, do you agree that you aren't friends with former romantic partners, and do you agree that you don't flirt with other people online, and do you agree that you share each other's passwords, that you know each other's friends, and that you have access to each other's accounts? And so these 3, the sharing passwords, and knowing friends, and accessing accounts, I called openness, and you're not friends with former romantic partners and no flirting, I call that fidelity. And you can see here there's an M and W. This is actually a multiple group analysis. So I looked at the same analysis in one moment, in one analysis, for both men and women. And what I kind of saw is that for both men and women, it's not about relationship satisfaction, but trust is hugely related to openness and fidelity and online rules that couples come up with. This one here was my actual dissertation. So in this one, this was with a big secondary data set. This is actually a dyadic analysis, so I had partners, male and female partners, so men and women, in matched couples. And I was looking at how their boundary crossing behavior, and how that impacted online intrusion, so checking up on your partner, and how that was related to relationship satisfaction and how responsive their partners were to their needs. So I was actually able to map out this relationship for themselves and also how it impacted their partners. And then this one here is a paper I actually just got published in the past couple weeks, where I again did a dyadic analysis. So I'm looking at partner 1 and partner 2. And then looking at those relationships about how online gaming, so how their frequency of online gaming, how that impacts dyadic adjustment. And dyadic adjustment is a relationship term for like how happy you are in your relationship, how well you adjust to problems. And then looking at the moderating effect of acceptability for gaming. So when you have this, now all of a sudden I can look at what this looks like in couples and look at this moderating factor. When you actually map this out, because you're going to have, remember when you do your moderation, you're going to do your independent variable times your moderator. I'm going to have it for just him, and then I'm going to have his gaming on her acceptability, her gaming on herself, and hers on his, and his on himself, and his on her. So it actually creates 4 moderating variables. So this is what this slide kind of shows you as the final results of that, where I have my 4 moderating variables, and then I have my predictor and my moderator in here. And then just like we do with all moderation results, like we talked about way back and more towards the beginning of the semester, is you'll create graphs. So I have graphs for each of my moderating variables and showing the interaction that's happening with each of those. So those are some examples of SEM that you can look at to kind of see what SEM looks like. But really there's a lot that you can do with this. Programs for SEM, and you can use Amos, M+, then there's some other softwares like EQS, Lisserol, and R. R is becoming more popular because it's a free software that doesn't cost any money. But you really have to, there's a pretty steep learning curve to R because it's very much based in coding. So Amos is the program that's attached with SPSS. So you can have a SEM product that goes along with SPSS. However, this program is really terrible. It has severe limitations on what you can do. Once you get into more sophisticated models, it is really limited on what you can do. It doesn't allow for missing data when you're testing mediation. So there's a lot of limitations that make it really limited unless you're doing really simple models. M Plus is really the software of choice of most statisticians, and it was a software developed exclusively for SEM. So this is the one you will most commonly see, and it's the one that I will also be using in the fall when we get into structural equation modeling. And another great thing about M Plus is that you can actually ask the developers, and this is a husband and wife power couple that developed this, Muthane and Muthane, who developed this off of a grant. And if you have a license and if you've purchased it, you can go on and you can ask them a question directly if you're running into problems, and they will answer your questions. Syntax in SCM or in M+. Syntax in M+ is really simple. You're going to have 5 main points or 5 main headers in here. You're going to have the title, so this is really what you call it. You'll have data, and this is where is your data actually at. The variables, so you actually need to tell M+ what your variables are called in the order of appearance. You'll understand why this is important in just a few minutes here. And then you'll have your actual model. So this is where you actually write out your model, and there's really just 3 commands. With means a correlation, so if I do satisfaction with trust, that means I want a correlation there. On means regressed onto. So you'll start with you kind of write this backwards, so you'll start with your dependent variable, on, and then anything that has an arrow into it, you write on one line. By is an indicator for a latent variable. So if I had, like that example earlier about your financial situation, I'd do financial situation by, and then write the 4 indicators that go with that. And then output is actually telling it what kind of output you want. And there's just a few common ones that you would often put here that I would introduce you to. Pretty much when you do this, when you go into SEM, the title, the data, the variables, and the output can all be done from drop-down menus, and all you're doing is writing out this syntax here. Some of the more recent versions of M+ also allow you to actually go into the software and actually draw it in there, and it will actually develop your syntax for you. One thing that's different in M+ from SPSS, so in SPSS you remember you end all of your commands with a period. In M+, it's a semicolon. So every command you end, you do with a semicolon. Also in M+, just like in SPSS, you can write notes for yourself. But rather than using the asterisk, you use an exclamation point. So you just use an exclamation mark at the beginning, and it'll turn a different color, and that's your notes. So just like in SPSS, you can write yourself notes. All right, so prepping your data for M+. So M+ is not SPSS, so that means it cannot use the SPSS data files that it saves at. So those like .save files that you see in SPSS, can't use it. M+ just wants the most simple way of data possible. It only wants the data and nothing else. So that means you need to have it in .dat form, and you need to take off the variable names from the data. That means you need to remember what order that they're in, which is pretty easy because you have it right there in SPSS. The third thing that you need to do, and this just makes everything easier, is have all of your missingness coded into a single value. Sometimes in SPSS, it'll actually code missingness as a blank value. M+ can't handle blanks or like the dots. So you just change it into a single value, and this is pretty simple. And I'm going to show you how to do that. Before you start converting your data over to be ready for SPSS or for M+, you want to make sure you have cleaned your data. You've done all that work that you need to do. Get rid of any variables you don't need. So as you've kind of seen, some of these secondary data sets have thousands of variables. Get rid of all of those and only have the variables that you need. It's going to make everything so much easier. And make sure that you have all your missingness entered correctly. So in that missingness column in SPSS, you make sure that all of those are entered correctly. So make sure you've done those things first before you're ready to get it ready to go into M+. So recoding for missingness. Let's cover that first piece, because that's the first step you're going to do is recode all of your missingness. For this, you go to transform and then go to recode into the same variables. And then what you're going to do is pull all of your variables over. You can kind of see on this one I left your participant ID over here because there are no missing values for participant ID. But I pull them all over, the whole chunk of them, and then I click on old and new values. Once I click on that, I'm going to click on system or user missing, and then I'm going to add a value. I always just put -99 because it stands out like a sore thumb and it's easy to see. And then you just click add. So it'll throw that over here, hit continue, and then you hit OK. So once you do that, you've now coded all of your missing to -99. And we're ready to actually save it as a .dat file now. So now that you're ready to save it as a .dat file, how do you do that? Go to File, Save As, and then you're going to go down here to the Save As type, click on the menu, go down to .dat. If you haven't taken away certain variables that you need to, you can click on this variable buttons and drop variables that you don't need. However, I really suggest you've already done that ahead of time. And then you just hit save. Make sure it's in the place you want to save. It's the name you want to, if you want to change the file name. I normally change it to something like M+ready, something that kind of stands out to me. One more step. So before that, you're going to click on this, make sure it's data, the .dat. You're going to name the file that you want, and then this box right here, you're going to unclick that. It will be clicked. It'll be a check mark here, so you want to uncheck that. That's going to take the variable names off the file, the file, which you don't want to have in M+, because it'll just cause a mess and it can't handle it. Now you have a data set all ready for SPSS. You're ready to go. So now it's time to practice. I'm going to open up a data set here that we've used before in class and show you how this works. All right, so this is the fragile families data. You have used this before in class when we've done logistic regression examples, and we just have a bunch of variables in here. So I'm going to show you, I'm going to do exactly what we talked about before. So here we have our missing values. So like on B5 temp here, let me go to that variable real quick. I've actually already set this one up for missing this. You can see here I've done the -99, which sticks out like a sore thumb when you do that. So I've already set everything to -99. But if I hadn't done that before, I would just go to transform, recode into the same variable, and then I'm just going to pull all my variables over, and then I'd click on old or new values and say system or user missing, make that -99, and click that over, hit continue, and then press OK. Now to actually, let's actually do this to make it work in this class. So I'm going to pull everything over, and I'm going to use -999. It's just to make something different than what I already have in here. So -999, add it in, continue, press OK. So now you can see here there are no errors, so that ran. And if I go over to the data view, you now can see that I have -999s all over the place. It sticks out like a sore thumb, so I know I did it, and I know it's good. Now I'm ready to save this as an M+ file. If there are any variables I didn't want to include, I would go ahead and delete these out. So like, let's say I'm not using these logistic ones, so I'm gonna clear these out. Let's say I'm not using race, so I'm gonna clear these out, and these are just the ones I'm going to use. Now I may resave this, so I'd save as, and save it just as it is under a new name. However, we're going to use this for our example here. So first thing I'm going to do is make sure I'm in a place that I actually want it to be in. I'm going to, just for the purposes of this class, I'm going to stick it right on my desktop. And I'm going to call this, M+ multivariate class example. I'm going to save it as a .dat file. Oh, there we go. Tab delimited. .dat tab delimited. Got to rename it. And unclick write variable names. That's all I need to do. You don't need to do anything with this encoding business over here. Just unclick that. Now it's ready to go. saving it to my desktop, I can click Save. Now I'm ready to go into M+. This is all it is. So if you remember, SPSS took forever to open. M+ opens right up in less than a second because there's really not much to it like there is with SPSS. It just starts off with this blank window. Now here on my laptop here, I have the free version of M+. The free version of M+ is really great because it actually gives you access to everything M+ can do. It just limits the number of variables you can include in your model. So it really gives you a good chance. You can download this for free and check it out to see how that works. So to start with, I'm going to click on M+, Language Generator. I'm going to do SEM with missing data. That's what you're pretty much always going to go to. I'm going to give the title of it, so class example. I'll go to browse, and if you remember, I put it right on my desktop. It's going to automatically look for just the .dat file, so there it is right there, our multivariate class example.dat. Go to the next one. Data format, you're pretty much always going to have, you're not going to include any of these missing data. You can say yes. And here you can add one variable at a time and actually add in your variables with what they're called. However, I'm just going to put in a couple examples and show you kind of a quick way to do that. And then there's a use variable list. So you're going to tell M+ what variables are there and which ones you're actually using in the analysis. Our missing value is going to be -999. And then if there are grouping variables, we can add that in here as well, or weighting variables. We're just doing analysis. You don't need to change any of this stuff. And then this is your outcome options. So if you want like modification indices, if you want, you're always going to want standardized coefficients and model estimated means variances. You can ask for missing data patterns, so it actually tell you what the patterns are across that. And I'm pretty sure that's about all you're going to really need for this. You can do more around here. Tech4 is a really popular option that people include. Alright, so you can see here it's going to give you a little error here that says, I haven't done the model for you. You need to do that. So here we have the title, the data, the variables, the analysis, output, and then the save data. That's actually new. You don't actually need that. But you're going to need to add in model and add in your model. So this tells us what we've titled. This is where the data is located. The names are, this is the names of the variables in the data set. So if we just go back over to SPSS, we can highlight these, copy them, and then we can paste this right over. So now we have all of our variables right here in the order that we told them that they were in, or that they were in. This is actually really important so that your results actually match your data. If you wanted to change the names of any of these, you can do that. Just like in SPSS though, you can't have spaces for names because then it thinks it's two variables. So here we have the variables in the data set. This use variables is which variables we are actually using in the data set. So let's say, for example, here I'm going to open up a new PowerPoint window, and what I'm actually going to do is draw out a quick model for you that we can look at. So let's say for this we're going to look at mother's engagement. So let's bring in a box real quick, because again we're not doing anything with latent variables here. So we can say, you know, M3 engagement, and then let's look at how, you know, like mother's and father's age impacts that. So let's just make a simple model here. So here we'd have CF age here, CM age here, and this model isn't going to make really any sense because it's not a real model that we're testing. And let's just add something in the middle just to kind of show you what this may look like with our syntax. So let's throw in let's just throw them M education, mother's education. So we would have in here mother's education going here, or mother's age, there. We'll have this one, and this one. So this is a pretty simple just mediation model where we have age here, education in the middle. So when you go to write out your model, you just write out exactly what we have here. So we're going to go backwards. So we're going to say M3 engage. So that's this one here. I'll copy that because we're going to use that variable. And you'll say on, and we're going to go back all the variables that are on it. So that's all three of these variables here. So we have those two and our M educate. It doesn't matter the order. I just like to put it in an order that goes backwards for me so that I can see it. And then you'll put a semicolon to end that command. And remember, we're going to be using these three here as well in our analysis. And then we also have two going on to M to the educate. So what you can actually do is copy this. We'll go to our next line and then put in on right there. And then if we wanted to account for the correlation here between these two variables, we can actually account for that as well by having a with statement between the two. And there we've done our syntax. You can see here, so the title, we've given the title, the data, we told it where it's at, we told it what variables are in here, we told it what variables we're using. Missingness is -999. This estimator right here is ML, tells us that we're using full information maximum likelihood. And we're going to get the residual and the standardized error. So now we're ready to run this. So you can go ahead and click run. It'll ask to save this file. So I'm not sure where I'm actually saving this. I don't want to make sure this is, so it's just going to do it right on the desktop. So run it. It asks you to save it, so it's saved that. And there we go, we're done. We've ran it. So it'll have all of your syntax there. Any errors it'll give you there. These aren't any errors to worry about with this, especially for this example. And then it's going to give you, we'll go down here. Here are all of your model fit indices. We'll cover those at a later time, but this is back when we're talking about model fit. We have a lot of different indices, and there's a little handout I'd give you that tells you exactly what you're looking for, what actually looks nice. And then we'll have our actual values. So our STDYX is your standardized value, so standardized here. So all of these estimates are your regression coefficients. And then you'll have your standard error, your EST over standard error, that's your t-value, and then your p-value. So this is very similar to what you would see in an output for SPSS. Alternatively, what you can do is you can ask for the diagram for your analysis. And so here we have the diagram. It just opened it right up for us, so it drew it for us. And we can have options in here where we just want the standardized results. We can ask for those. We can take away anything we don't want to see in here, but it'll tell us exactly what our results are. So here you can see here's our error in here, and there's our value. To see the significant, so I can say show only the significant ones, and these are actually our significant values. So you can actually see by looking at the output in here, or you can do it by the table. So there is your introduction to SEM, a very brief, quick introduction. If you want to learn more about this, I highly encourage you to enroll in the class in the fall. We'll take a lot more time getting into this so you can feel confident in doing it. For those of you going into the fall, this is what we're going to get into when we go into SEM.